Okay, class, our discussion now is on hemostasis. Stasis of blood flow, stopping of blood flow. Now, one thing when we think of hemostasis, I must say, you would think of that you get cut and you stop bleeding. Hemostasis occurs all the time. As you move around, and I move around, just moving our arms, our legs, moving, pulls on those delicate blood vessels. Therefore, all the time we're having microvascular breaks in our blood vessels. As I alluded to in my platelets video, that the platelets need to plug up these holes, but the other portions of this, players in the hemostasis game, also need to be present to help out. So hemostasis is not just when you get the occasional cut, whether it be mild, moderate, or severe, but it's happening all the time. So now we want to look at it and investigate what is hemostasis. Hemostasis is a series of reactions that stops bleeding. Okay? There are three events that occur in hemostasis. The first event to start is vascular spasm, where you have immediate vasoconstriction to stop. The second is platelet plug formation, which we discussed in the platelet section. And then coagulation, which we call blood clotting. Now, note that a lot of people would think that clotting is the only thing that stops you from bleeding. It is not. It's one aspect of it. All right? Vascular spasm is where the blood vessel starts to spasm to try to at least slow down the flow. It won't completely stop it, to slow it down. What causes the vascular spasm? One is disturbance of myogenic tone. That brings up the term, tonus of muscle. Tonus. Tonus is resting muscle tension. On your biceps, if you're not using them right now and you push on yourself, you'll have a certain amount of firmness. That's a street term, firmness. Technical term, tonus. That was caused when you studied in ANP1 by the muscle spindles. What's the purpose of tonus? What's the purpose of having a resting muscle tension? If we were in class and someone entered the room immediately with means to harm, then we would want to try to jump up or defend ourselves. Well, if our muscles had no tonus, it would take too long to activate. So we want this. With no tonus, there's what we call flaccidity when it comes to skeletal muscle. But let's go back to smooth muscle. In the blood vessels, you have this smooth muscle. And what will happen is, if the blood vessel is cut, you will disturb this tone and it will try to contract down. You also, when you damage the blood vessel, endothelial cells, the lining cells, start to secrete small secretions known as local paracrine secretions. One is endothelin, which is a vasoconstrictor. All of these actions are an attempt to vasoconstrict and slow down the blood flow. Platelet plug formation. We don't have to say much on that. We already did that. We said that the platelets was second in line, but they played a pivotal role in not only vascular spasm, but also coagulation. Because what the platelets initially are going to do is form a platelet plug, like a cork. But when they start releasing some of their chemicals can help with vascular spasm, and they even have a few clotting factors in them. Okay? So the platelets are very vital in the whole role of hemostasis, as we alluded to earlier in a video. Now we come to coagulation. Okay? Coagulation is basically a set of reactions in which blood is transformed from a liquid to a gel. There are what we call three pathways in this: an intrinsic, an extrinsic, and a common. Let's look at that. Three pathways: an extrinsic, an intrinsic, and a common pathway. The common pathway is the one that gives the actual clot. The common pathway. Now, note my arrows here. This arrow is a little shorter than that arrow because the number of steps in the extrinsic pathway is less than the number of steps in the intrinsic. So that's the reason that I have it that way, because of the difference in the steps. All right, and then the common pathway. So they both come together and give the common pathway. Okay. Here are our clotting factors. Now, remember what I said. A factor is a substance that someone discovered, but they didn't know the chemistry of. And so they gave it a factor name. Later, it was given an official name. Now, notice that the factors are in Roman numerals. Now, this is something of importance to note. The factors came about at the time of discovery. So this would have been the first one discovered, then this one. So they were put in time of discovery, not time of in the reaction, you'll see. That means the Roman numerals are going to be out of sequence, because you may have discovered something and then all of a sudden found, oh, there's something that goes in between that. Well, if you renumbered around the world, they'd be all confused. So sometimes you would come and you would find that, oh my, maybe 10 years later, the clotting factor we thought was a clotting factor was actually two other clotting factors we found. So what are you going to do, renumber? No, you just take it out. So look at clotting factor 6. It has the death symbol, which means they found later it didn't exist because it was two other clotting factors. So these are the clotting factors that we have up to now. All right, so we go further. We have classes of clotting factors. Now, clotting factors are basically proteins. Proteins, as you know, are made, and what happens is with these particular clotting factors, some of the enzyme action to make the clotting factors, let me come back, some of the enzyme action to make some of the clotting factors need certain substances, or to activate them. So for example, clotting factors 2, 7, 9, and 10, you need vitamin K. Vitamin K is required by the enzymes that make the clotting factors. Mike, where are the clotting factors made primarily? In your liver. That means when you have a liver problem, then you are going to have problems making adequate clotting factors. That's one of the problems with cirrhosis and hepatitis. So some of them are thrombin sensitive, you'll see, and some of them are vitamin K sensitive that we'll chat on. Okay. Coagulation versus anticoagulation. Now I'm going to go back here to the clotting factors. You see how they have the word procoagulants there? That means for coagulation. For coagulation. I'm going to say, and let me kind of explain how that works out. It is important that we do not form inappropriate blood clots. Inappropriate blood clots can lead to sudden death. If a clot, we call a thrombus, sitting clot, forms in the circulation, it could break free and travel, called an embolus, and block the circulation in vital organs, particularly in the lungs. It's called a pulmonary embolus, and it can kill you right away. Okay, so we don't want to clot inappropriately. However, if we do get a cut, a particular major cut, or even under normal, we need to clot quickly. So we need to be able to keep the clotting factors from not inappropriately activating, which would then lead to a clot inappropriately and could kill us. But when we do get cut, we want to be able to clot very quickly for these clotting factors. Okay. So that when we do not form inappropriate blood clots, we have anticoagulants in the blood. So the nemesis to procoagulants are anticoagulants we have floating in the blood we'll talk about. This, along with other mechanisms to determine homeostasis, is in place to prevent inappropriate blood clotting. When we do get cut, we wish for our clotting to occur quickly. Thus, clotting occurs using a physiologic, enzymatically converted cascade that involves positive feedback. Clotting occurs quickly. All right, let's look at this little demo, this here, that I've put together. All right, this is a generic, and this is using it in terms of a clotting factor. Okay, we have a proenzyme A, which would be synonymous to an inactive clotting factor A. Some kind of way, something activates it. Something gets it activated. When it gets activated, it becomes an activated enzyme A, or an active clotting factor A, using it in the clotting factor. Now, down here, we have an inactive enzyme B, going to an active enzyme B. Okay? Second entity. In this particular case, though, we took a proenzyme and made it an enzyme. This enzyme, though, is acting as an enzyme to catalyze B to active B. Then, if I come here, we make an active B, and it acts to catalyze an inactive C. So you're activating an enzyme, and that enzyme acts to activate the subsequent enzyme, which activates the subsequent enzyme. So this becomes a cascade reaction, a cascade. See, over here I'm showing it as far as clotting factors. Same thing. So when I say enzymatically cascade converted, then that means that you are activating, and the first thing to get it started is something has to activate the initial clotting factor in the pathway. And once it's activated, it should be a snowball effect that should then continuously activate the others in a sequential fashion. Now, we said we want it to happen quickly. So thus, we need positive feedback. Okay? So let's take the assumption that active clotting factor C, or enzyme C, can come in and act as an enzyme retrospectively on A. What would that do? Once you form this, you still have this going. That would enhance the effect. That would give a tremendous positive feedback, so you would develop these clotting factors very quickly. Very quickly. So that's the generic. So in the circulation, you have procoagulants, which are inactive clotting factors, and you have anticoagulants, all in an attempt so that you don't clot inappropriately, start throwing a blood clot. But if you do need to clot, you need to do it very quickly. And so you'll use a cascade reaction enhanced by positive feedback. A cascade reaction enhanced by positive feedback. So that's the generic of how everything works. Okay? Now I'm going to end this video here. This is going to be clotting factor video 1. And then we're going to actually go into the clotting factors in video 2. Okay? All right. Thank you there.